Good morning, Science 20s. Our lesson today is on energy flows in an ecosystem. We will be looking at the concepts of trophic levels, food webs, food chains, pyramids, examples of autotrophs and heterotrophs. We'll also be comparing why population size is different based on biomass, pyramid of numbers, and also the energy pyramid. So we have to ask ourselves, where does the energy come from for food webs, food chains, everything we're going to look at today? We know energy is the ability to do work, but the question is, where does all this energy come from? And the answer is very, very simple. The energy comes from the sun. So, if I take a look at how energy flows in an ecosystem, it all starts with we have organisms. And one of these organisms would be a producer. Producers are things that use the energy from the sun to produce food. Okay, so these guys get their energy from the sun, like plants. Now, something that would eat a producer is called a consumer. Consumers get their energy from other organisms, from eating, let's say, producers. Now, there are many types of consumers. If you were the first consumer, the one that gets its energy from eating the grass, you are called a primary consumer or a herbivore. If you are something that eats a primary consumer, you would be called a secondary consumer. If you are something that eats a secondary consumer, you would be called a tertiary consumer. And then we can even go farther than that. If your chain is so long that you eat a tertiary consumer, you could be, let's say, a quaternary consumer. In the category of consumers, though, we have other little subcategories. So if you only eat meat, so you strictly eat other animals, other meat creatures, you would be called a carnivore. That could possibly be if you have Mr. Parker as a teacher. He likes to call himself a meatitarian or a carnivore. But most humans would fall under the omnivore category, meaning, yes, we eat meat, so yes, we're a consumer, but we also eat plants. We also eat producers because we eat lettuce and we eat vegetables and we eat fruits. Therefore, we are an omnivore. There's a third larger category, and that's called a decomposer. These are organisms that break down complex organic molecules into simpler molecules. This would be something, let's say, like a bacteria. And then we have scavengers. Scavengers intentionally feed on dead or decaying or rotting matter. They do not kill things for themselves. This again would be something like, let's say, a buzzard. So, what I want to do is I want to take each of those categories and look at them a little bit more in depth. So, I have a picture here of Bouchard Gardens in Victoria, British Columbia, one of Mr. Kemp's favorite outdoor gardens he's ever got to visit. Well, this is a perfect example of a producer, an organism that uses energy from the sun, light energy, to make sugars and other organic compounds so that it can go through the process called photosynthesis. Any plant, bush, flower, grass would be a producer. They get their energy from the sun. They are also called autotrophs because they produce their own food. They don't have to hunt down food. They use the energy from the sun to make their own food. Therefore, they are called autotrophs. They automatically produce their own food. On the other side of autotrophs is heterotrophs. These guys can't produce their own food. They have to go out hunting to eat something. So, a primary consumer is an organism that eats green plants, algae, phytoplankton, depending if it's in the water or on the land. These guys are herbivores. They go out looking for plants, looking for herbs. They have to, if there's no food in their area, they have to move on, like the buffalo would go looking for more food to go grazing. It would move looking for that. That's why it's a heterotroph. A secondary consumer eats primary consumers. So usually this is somebody who eats herbivores, right? So this would be, let's say, a cow. A cow needs to eat a herbivore, but also would eat primary consumers. And these guys could be, so these guys would be meat eaters as well. So these guys are eating those creatures that eat only grasses. A tertiary consumer eats a secondary consumer. Now, it is possible that they will also eat grasses and stuff, because we might fall up here in this category. We eat lettuce and stuff, so we would eat producers. But again, we could eat rabbit, we could eat fish, so we would eat other animals below us. Scavengers is the weird one again. These are the animals that literally go out of their way to feed on dead and decaying things. Beetles, worms, magpies, and I've already said vultures. A decomposer is different than a scavenger. This is an organism that grows in or on decaying matter. This would be bacteria, fungi or fungus, mold. I love this because this is a time-lapse picture of an apple taken with a bite out of it, and we watch it over time. Let's watch the picture of the apple. Gonna speed it up a little bit here. Here's our apple. And I love time-lapse videos because it completely shows our apple from day one as it goes through this process. So we can see it's got a little bit of mold. It's starting to grow some bacteria probably in there already. The mold is taking over. And it's going to be, the purpose is to break down this matter so that the nutrients can go back into the soil and other organisms like trees can absorb those nutrients from this decaying matter. Soon we're going to see it starts to change shape as it breaks down farther and farther. This is kind of like how your compost pile at home, if you have one, does work. Well, if we look at energy in an ecosystem, we're going to see a lot of these pyramids. There is many different types. We're going to look at a few here in Science 20. The first thing we have to understand about looking at a pyramid is there are things called trophic levels. At the bottom is our first trophic level, then it goes our second trophic level, our third trophic level, and then our fourth trophic level. Trophic levels are divisions of species within the ecosystem based on their energy sources. So if we take a look at the bottom here, we will see that this is where 100% of our energy is. That energy, remember, comes from the sun. So if the sun puts out 100% of our energy, notice the flowers, the grasses, the bushes, the trees, it only gets 1% of the energy, because not all the energy makes it there, right? Some bounces off our stratosphere, others of it gets used for other purposes. So the the producers at our first trophic level, they get 1% of the energy. And once they get 1%, now from now on, when a grasshopper eats the grass, it only gets 10% of the energy prior to it. So instead of 1%, move the decimal place. The grasshopper only gets 0.1% of the energy that the grass had. The yellow warbler, a bird, gets only 0.01%, 10% of the energy the grasshopper had. The peregrine falcon gets 0.001, only 1% of what the yellow warbler had. Now, it doesn't seem like this makes sense at the beginning, but think about it. The grasshopper only gets 10% of what the flower had because the flower used some of this energy. The flower is reproducing, the flower is growing, the flower is producing food inside of it like sugars to be able to go. Well, we say to ourselves, well, what's the grasshopper doing that it can only pass on 10% of the energy it got from the coneflower? Well, remember, it's got to have a heartbeat, it's got to breathe, it's got to move around. So the energy is going to get used. So when an organism eats an organism from a lower trophic level, it's only getting 10% of the energy passed to it. This is why a grasshopper doesn't eat one or two blades of grass in a day, it eats many blades of grass. Where a warbler doesn't eat just one grasshopper because it's only getting 10% of that original energy. Instead, it's going to eat many grasshoppers or other food sources as well. Let's watch a simplified version of this and see if we can think of trophic levels with our areas of producers, consumers, and inside consumers. We have herbivores, omnivores, and carnivores. Oh, I goofed on that. I hit the wrong button.
Producers are autotrophs that capture energy from the sun to make organic molecules. There is an exception, though, and the exception are the chemosynthetic bacteria that can make organic molecules from chemicals in hydrothermal vents and don't require the sun's energy to do so. Consumers are heterotrophs and get energy from eating other foods. We can break consumers into more categories as well based on their diets. Herbivores, like grasshoppers, will eat only producers. An omnivore will eat producers and consumers, like a bird that eats seeds and insects. Carnivores eat other consumers, and decomposers will break down all dead organisms from every part of the food chain, which is why it's written on the side of this diagram. Detritivores are a specific type of decomposer, which feeds on detritus, which is fecal matter or decomposing organic matter. Each trophic level on this pyramid indicates the organism's position in a sequence of energy transfers. Producers are at the bottom because they support all the levels above. They get their energy from the sun, and that energy gets transferred to the organisms that consume them. We can follow the energy transfer by looking at a food chain, which is a single pathway of feeding relationships among organisms in an ecosystem that results in energy transfer. Arrows are used to show the direction of energy transfer, so it goes from the food into the mouth of the eater. Food chains are a great way to follow energy transfer, but in reality, a food chain is oversimplified. A food web consists of interrelated food chains, and it's a better representation of reality. You can see all the different organisms in an ecosystem or habitat and how they relate. The amount of energy that gets transferred from one level to the next is surprisingly small. Only about 10% of energy from the previous level is transferred to the next each time. Most of the energy is lost as heat or metabolic and digestive waste as the organism lives its life. Luckily, there are lots and lots of producers at the bottom level to supply the energy needs further up the pyramid. This does mean, however, that as you go up the pyramid, there will be fewer and fewer organisms that can be supported by the level below. That's why there are so few eagles compared to sparrows or grasshoppers in any given ecosystem. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe.
So I love that because it explained the pyramid of energy as decreasing and you're only passing on 10% of the energy. And again, it talked through why does it only pass 10%? These organisms are living their own lives. They're going to lose a lot based on heat, but they also have to run all their metabolic systems, and so they don't get to pass a lot. It's not like this the grasshopper is just going to sit in one place. It's going to expend some of this energy. Now, besides the pyramid of energy, we also have something called the pyramid of numbers. We will notice it still goes first trophic level, second trophic level, third trophic level, and fourth trophic level. However, the pyramid of numbers is based on population size. So we will notice that at the bottom, the wider part, where there was more energy before, we also have more individuals for number of population. So we have millions of blades of grass, thousands of wildflowers, hundreds of little shrubs. And so, what eats millions of these blades of grass? Many, many grasshoppers. And a yellow warbler doesn't eat one grasshopper. A yellow warbler eats many grasshoppers. And a falcon eats maybe a yellow warbler. So we can see we can support two falcons at the top, 500 birds, spiders, those secondary consumers in the middle, hundreds, 1,000 grasshoppers, ground squirrels, and other things at the primary consumer, and then millions and millions of grasses and shrubs and wildflowers and stuff as a producer level. So again, bigger numbers at the bottom, just like a pyramid would say. Down here, even though it's a large geographical area, again, we can only support so many larger animals up at the top. There's only so many deers that can survive in a region because eventually we run out of, look at how much more food it needs these to support these bigger animals down here for a producer. You eventually run out of food. And so organisms either have to move on or there's not enough food and the organism passes away. There is a limit, though, to these pyramids of numbers, and that is because they don't take into account the size of individual organisms. So we have a third pyramid that takes into account size of organisms, and that is the period of biomass. Biomass is based on the amount of dry mass of living or once living organisms. So this is if we were to dry out, and so when the animal decays, if we take up all of its dry mass, its bones, and we weighed it, we would see that, notice again, we dry out grass, and we know if you've ever left your grass in your lawnmower and let it completely dry out, it does have a lot of weight. Think about how many individual pieces of grass is in there, right? For the quantity of grass. Now we weigh it. 3,000 kilograms of possible cornflowers or grasses compared to 2,000 kilograms of grasshoppers, or 15 kilograms of birds, or 1 kilogram of peregrine falcon. We can see that the pyramid of biomass is we weigh, and we can see that we're going to have less up here, right? If we even put 2 deer in a forest up here, well, that would weigh way less than all the leaves and grasses we add together, because there are millions and millions and millions of those. When you first think of it, oh, an elephant weighs a lot, yeah, but then add all the grasses and stuff together in that region, it would weigh a whole lot more. Well, as the previous video said, a food chain is a simplified region, right? We have an organism here, something eats it, something eats it, and something eats it. We usually fall up here at the high end. We eat other things. Nothing eats us intentionally. Can something attack us if it really was hungry? Of course it could, but we are at the top of the food chain. Again, arrows point to the mouths of what's eating it down below. So what I would like to do is let's watch this goofy little video.
Today we visit one of the most unhealthy environments in all the world, the wild Formica Plains. Though this land is sparsely populated and completely unsuitable for most forms of life, herds of chicken nuggets are a common sight. The chicken nuggets range these open surfaces in search of small pools of barbecue sauce like this one. But they are not the only inhabitants of this harsh land. One of their many natural predators is the quarter pounder with cheese. The chicken nuggets have heard him approaching. They sense danger, but with their poor eyesight cannot tell precisely where he is. The cheeseburger waits for just the right moment. Then, without warning, he attacks. One unfortunate chicken nugget struggles in vain to free itself from a patch of honey mustard. The cheeseburger quickly seizes his quarry. For today, the cheeseburger will not go hungry. But tomorrow's hunt for a side of fries will be yet another link in the fast food chain.
Now, if we think about this extremely cheesy video that we just watched, a food chain could possibly be, hey, we had barbecue sauce and we had chicken nuggets eating it. And remember, the chicken nuggets were scared because quarter pounder with cheese eats them. So, quarter pounder eats chicken nuggets, eats barbecue sauce. This is a food chain. However, it's overly simplified because chicken nuggets do not only eat barbecue sauce in this video. We saw that they also eat honey mustard. And we saw that quarter pounders don't only eat chicken nuggets. We saw that cheeseburgers also eat chicken nuggets. And that it alluded at the end of the video, tomorrow cheeseburgers might go hunting to eat some fries. Well, when we're following this path, quarter pounder eats chicken nuggets, eats barbecue sauce, this is a food chain, simplified one steps. However, in the big picture, things eat more than one thing. So cheeseburgers eat chicken nuggets and fries. Chicken fingers eats barbecue sauce and honey mustard. This is a food web. It's much more complex, and most organisms eat more than one thing. For instance, humans, we eat probably hundreds, if not thousands of things when we make them in combinations for different recipes and such. So here are some food chains, simplified food chains from fresh water. So the northern pike eats the dragonfly larva. The dragonfly larva eats the mosquito larva, and the mosquito larva eats algae. Well, since algae gets its energy from a sun, it's a producer, and we could also call it an autotroph. It produces its own food. Primary consumer gets its energy from a producer, secondary from a primary, tertiary from a secondary. So these guys would all be heterotrophs because they get their energy from hunting down their own food. Oh, went too far. Another food chain we have here is prairie grasslands, and we know this one a little bit better because we live in Medicine Hat, where we have purple coneflowers. Grasshopper eats the coneflower, yellow warbler eats a grasshopper, peregrine falcon eats the yellow warbler. Again, coneflowers get their energy from the sun. That makes them a producer, so they are an autotroph. They automatically make their own food source. They do not get to go, ooh, I need food, so they pick up and cross the street. Where all three of these organisms, these guys are going to be heterotrophs because they hunt their food. So primary consumer eats producers, secondary consumer eats a primary, and a tertiary consumer eats a secondary. Well, what I want to look at for a second then is DDT. Now, I don't like the order we have these slides, so I'm going to jump one and just look at biomagnification first. So biomagnification, if you remember from previous studies, is the accumulation of a toxin up the food chain. So it comes in at, let's say, primary consumer level, and then it takes off from there.
Let's examine how human actions may impact pond species. For example, if there is improper waste disposal, spilling toxic chemicals into a pond and killing off the algae, it will decrease the number of herbivores, which will then decrease the number of top-level carnivores. In this case, the more toxins you have, the more the herbivore population decreases, which in turn decreases your predator population. Biomagnification is the increase in concentrations of harmful substances in the environment as they pass through successive trophic levels of food chains and food webs. When even larger fish eat those tiny zooplankton feeding fish, the larger fish contain an even greater amount of toxins in their body. By the time top-level predators like cranes consume the toxic fish, the crane's body becomes so toxic that their ability to function, reproduce, or live full-length lives may become impaired. In other words, organisms at low trophic levels ingest small amounts of toxins, which magnify as animals on the next trophic level consume those low-level organisms. And this effect will grow with each succeeding trophic level. Bioaccumulation is the increase in concentration of harmful toxins within an organism. For example, if a fish is continually exposed to toxins throughout its lifetime, it may experience chronic poisoning and a shortened lifespan. The impacts of toxins are unique and may impact an organism in very unique ways. It's also important to remember that different toxins impact different elements within an ecosystem. One type of toxin may impact animals directly, while another may have indirect effects through bioaccumulation or biomagnification, killing off top-level predators. The impact of most man-made chemicals are still unknown, particularly the long-term impacts of these chemicals. If we continue putting chemicals into the environment and allow those chemicals to biomagnify, the impact may have extreme effects on humans as well. Our actions, and even our thoughts and words, have an impact on the world around us. It's not enough to discuss the impact of humans on the environment. What's lacking is compassion and the understanding that we are deeply connected to nature. Only when we come to love and respect nature will the planet have any hope of surviving the current 6th mass extinction.
So, one toxin that you probably remember from grade 9 is we talked about DDT. DDT was a pesticide used in the 1950s to kill mosquitoes that were spreading diseases. DDT, though, does not break down into less harmful chemicals, or not easily. And so what happens is it gets trapped in the environment and it builds up and it builds up, and that's called biomagnification. It concentrates in the fatty tissues of organisms and humans, and it stays in the environment for a long time so that as it can build up in your system and cause health defects later on. Let's take a look at a short video.
It begins with the war-born development of DDT. This diabolical weapon of modern science saved millions of humans, but killed billions of insects. Man, with this newly discovered force, has at long last gained the upper hand in our age-old struggle. The really heavy blow fell only a few months ago. It came from laboratories where top scientists from famous universities and from industrial and government organizations collaborated to develop something new and different. They succeeded. They perfected Pestroy, the most effective weapon man has ever wielded against insects. In both its forms, powder and liquid, Pestroy means doomsday to us insects. For this new insect destroyer contains a lot of DDT, not just a little. Its DDT content is even higher than government specifications. But the really sure kill feature of this insect killer isn't simply that it contains DDT, it's the way that it makes sure that bugs get the DDT that's in it. For example, take this liquid form, Pestroy DDT synthetic resin coating, ideal for vertical surfaces. It's brushed on easily and quickly and dries in half an hour. It forms a clear, long-lasting protective coating, scarcely noticeable on most surfaces. Other preparations, sprays for instance, not only irritate the nasal passages and fog up the atmosphere, but quickly lose their effectiveness as the fog is dissipated. As a result, spraying must be repeated time after time. But not so with this. Pestroy goes right where it should go to kill insects. And once applied, it keeps right on killing them. Week after week, month after month. Here's why. It's compounded with a new type of synthetic resin which binds DDT to any surface, makes it cling, keeps it from brushing off or blowing away. After application, DDT particles form at the surface of the coating, right where the insects walk, creating a long-lasting booby trap for insects. These crystals stay put. They are densely matted, not spindly and loosely knit, not easily shaken off or blown away. Pestroy liquid coating can be applied wherever insects are found. around doorways, for instance. On screens, where it not only kills insects, but also tends to keep the screen wire from rusting. In lockers, where bugs always go in search of food or clothing. On fruit and vegetable stands. In cupboards, the happy hunting grounds for all types of insects. On tables and benches at picnic grounds.
So you guys are beginning to get the point. We have talked about DDT in grade 9 extensively and looked at, yes, it had good cases because it stopped the spread of malaria. However, it had a lot of negative effects because it was one of those things that accumulated, especially in, let's say, like birds' bodies, the bald eagle in the United States, and limited their ability to reproduce. The eggs that they laid had shells that were significantly thinner and broke, and therefore it became a really big scare because that national bird, the bald eagle, became closer to endangered. Here, it would have been the peregrine falcon, and they became vulnerable in Alberta. And so, again, legislation put in DDT is no longer used, and we kind of went from there. But it stayed in the environment for a very, very, very long time. Now, before we finish up, I have a picture here of a food web. And what I want us to do is, what do you think the relationship is between the great horned owl and the rabbit? What is their relationship? Now, if you said their relationship is predator-prey relationship, you would be correct. The owl eats the rabbit. What do you think the relationship is between the great horned owl and the fox? Because the horned owl doesn't eat the fox and the fox doesn't eat that. So let's take a look. The horned owl eats a bunny, and so does a fox eat a bunny. The horned owl eats a squirrel, and the fox also eats a squirrel. A horned owl eats a mouse, and the fox eats a mouse. So what is their relationship? And again, if you said their relationship is competition, you would be correct.